So another adaptation that actually links to bradycardia and cardiac hypertrophy is the impact it has on the cardiac cycle. And therefore, because the heart increases in size, particularly the left ventricle and the chambers, it allows therefore a greater stroke volume, and as we said, bradycardia, the lower heart rate, resting heart rate particularly, of 60 beats per minute. So then this contributes to having a greater cardiac output, and so this then means the athlete can work at their intensity needed. So in aerobic they can work for the longer intensity at the lower intensity for a longer duration more easily. And so the increase particularly of the left ventricle for the cardiac hypertrophy also has an impact on blood pressure, and because it lowers the systolic blood pressure value, this means that the arterial pressure is less because of this increased stroke volume. Means we can pump a larger volume of blood out of the heart without the heart having to pump as vigorously and as often as before, leading to the increased cardiac output, as we said. And then the increased blood flow actually leads to an increase in blood volume, which we're going to come to in a bit. And these adaptations overall just allow the cardiovascular system to become more efficient. So when delivering oxygen to the muscles, it's more oxygenated, so we can have more oxygen available to the muscles. And this diagram here also just is about Starling's law of the heart, and that if we can increase the end diastolic value and the venous return, that we can maintain stroke volume and cardiac output. So then they can increase, which will eventually actually help us in our sports. And here is just a slide showing the cardiac dynamics of exercise, and that in different sports we need to actually understand that this can actually change, and depending on the athletes also. We can work out our cardiac output by the equation stroke volume times heart rate. And this is another adaptation of increasing the cardiac output, and this is the volume of blood pumped out of the heart per minute. And as we said, we can calculate this referring to the table on the screen. So we can see these are typical values of heart rates, stroke volumes and cardiac outputs at rest, moderate exercise and maximal exercise. And we can see that a typical heart rate at rest is between 70 to 72, but this can obviously, resting can be 60, it depends on the fitness level of the person. And then this can actually increase to 100 to 130 beats per minute. And we can work out the maximum by taking 220 minus the age of the athlete. Obviously we can see that we've also got athlete examples, and we can see that some athletes elite level athletes can even have a lower resting heart rate of 30 beats per minute, and then moderate 65. So these adaptations of the heart can actually lead to these values being increasingly lower than just normal performers. But it's important to know that it's mainly a result of an increase in heart rate which affects the cardiac output, because stroke volume does increase but only to a point, and then it cannot increase anymore. So the main changes are due to the maximum heart rate, which is the 220 take away our age. So it shows that for a typical athlete of 17 years old could actually reach a heart rate of an age 20 athlete could reach a heart rate of 200 beats per minute. So when we increase our heart rate by a lot and our stroke volume by a little, we can actually result in an increased cardiac output. So by an endurance athlete taking part in continuous training will require a high level of respiration, and therefore this requires more blood to leave the heart, and therefore over a period of several weeks and months the athlete will benefit from this, as their hearts will not need to pump as vigorously in order to circulate the same volume of blood. So they will not be working as hard, and therefore this can benefit their performance, so they can prolong the effects of fatigue, which will put them in a better position of performing better in the marathon race. And we can see that our cardiac output actually nearly doubles in capacity when we actually exercise, because of the demands of oxygen needed by our muscles and our vital organs. the heart actually has to become more effective in pumping oxygenated blood around the body. So these adaptations can really benefit the performers. So here on the screen we have two graphs from our investigation data. On the right we have our heart rate in the continuous steady state exercise. And we can see that from rest, this participant's heart rate was around 72 beats per minute. From the rest of the pre-test, we can see an anticipatory rise until their heart rate's around 86 beats per minute. And as the incrementals increase slightly from 5, 10 to 15, we can see that the gradient actually starts to plateau, and that it actually only increases from around 98 beats per minute to around 102, so it's not a very large margin of an increase. But then at the post-test we can see that the athlete's heart rate is around 110 beats per minute, so it's slightly elevated, and it remained elevated for a period after this. So long-term adaptations to an athlete would mean that their post-training values would be lower. So, and we could do this by measuring the recovery time to see if the heart is able to respond to the situation and recover faster. And this is normally measured by seeing how many minutes it takes the heart to return to their resting exercise and their resting values. So an athlete whose heart rate returns to exercise much more quickly, therefore needing a shorter recovery, would probably have a better overall fitness level than someone whose heart rate remained elevated over a period of time. So the post-training values would be lower. And also an athlete who's undergone long-term adaptations of training would be able to sustain their heart rate. So this athlete is has quite good overall fitness because they're sort of maintaining their heart rate. It's only actually gone up from around 78 and to 110, which isn't actually that much, because they're working aerobically, which is what we would expect to see. They're working within their aerobic threshold. But long-term adaptations, we should see that their heart rate actually returns to near the resting at the post-test, and in this example we don't actually have that. So we probably, in order to improve this, would actually measure after post-test, a couple of minutes after, to see how the recovery actually decreased and whether it decreased to around the resting heart rate level. And this links to the idea that heart rate range allows you to work even harder. So by lowering working heart rate is actually advantageous. By decreasing a resting heart rate shows a better level of fitness, and this links the idea to the stroke volume, because if the heart can pump out more blood per beat, therefore the heart doesn't need to beat as frequently as it's used to, which is advantageous to life in general, maintaining our health. And in terms, not just as sports examples, but also in life as well. And the graph on the left shows the blood pressure values during the multi-stage fitness test. And this test actually involved increasing the level, the incrementals, to make it harder for the individual. And we can see that the values at rest were 102 systolic blood pressure over 44 diastolic. And this is actually typically quite low. The typical blood pressure value is 120 over 80, so this could be an anomaly, or it could be just the athlete had a high level of fitness. And we can see that it started to gradually increase until level 4, when we saw quite a big increase in the diastolic blood pressure to 121. And then we started to see a decrease, which maybe is starting to show that the athlete is starting to work anaerobically. They can't maintain this intensity, it's high intensity working at it, so therefore they're forced to work aerobically and therefore decrease the amount of how the heart is working to pump around the body. So lower blood pressure, specifically systolic values at rest, will increase during exercise, typically, what we expect to see, but fitter people will see their blood pressure return to their resting levels faster. A lower blood pressure means there is less pressure in the blood vessels, and this is the force at which blood is travelling through. So a lower blood pressure means the force flows more easily with less resistance and force. Obviously, if we have hypotension and hypertension, it can be bad, and we can start to see negative effects on our health. But in exercise, as we've said, you have to expect blood levels to increase, blood pressure to increase. And we can see that actually at the post-test, our blood pressure levels actually went up to 124 over 97. So if long-term adaptations of training would actually show that the value should return to rest much quicker, and they've returned pretty much to the average value of 120 over 80, but at resting it was 102 over 44, so we can't actually determine, because of the results, what the actual level was. But yeah, we would expect with long-term training that the blood pressure would return to resting at a faster rate and recovery. And another point to add on to this, to do with the heart rate, is that long-term training actually causes an increase in the parasympathetic activity of the heart. So the sinoatrial node is responsible for firing the impulses in order to allow the atria to contract, so the blood can move into the ventricles into the next phase. And training actually decreases the rate at which the impulses are sent. So this is how heart rate is actually lowered. So by training, you are actually lowering and decreasing the sinoatrial node's rate of production of the impulses. So you actually see a decrease in the resting heart rate. And linked to this is cardiovascular diseases. Before we go on to that, I just want to mention that some more adaptations that sort of relate to this, and this is the idea of capillarization. Through training, we can actually increase capillarization and the amount of capillaries that we have in our body to make them more efficient. So capillaries carry the blood through the muscles and the organs, and the capillary density is the number of capillaries that supply nerves to the muscles. When you exercise, your capillary density will increase, and this is the idea of capillarization. By having more capillaries, we will have more red blood cells to carry more oxygen. This means that there is more blood flow, which means that there is more oxygen that can be pumped to the working muscles. The capillaries are also very important in playing a role in the greater removal of carbon dioxide and lactic acid, so making gas exchange more efficient, and we can increase the numbers of oxygen being exchanged into the body and the amount of carbon dioxide and lactic acid being exchanged out. And this is sort of to do with our blood volume. So hematocrit, which is the red blood cell count, means we are having more oxygen carried by the hemoglobin. By having more red blood cells and hemoglobin, we can transport more oxygen to the working muscles. And through training, we can actually increase our red blood cell count. And as we previously mentioned in the video, with altitude training, this is a strategy that aerobic athletes would use in order to increase their red blood cell count to carry more oxygen. And then by having it to do with the lower blood pressure and having blood flowing more easily through the vessels means that the blood will have a better viscosity. By having a better viscosity means the blood is more viscous, it's more easy to transport because it's less thick. So therefore it's thinner in the blood vessels and there's less resistance then being put on the walls of the blood vessels. So the blood flows through much more easily without the resistance, and therefore it can get to the muscles and deliver the oxygen at a faster rate. We don't have to worry about sort of what's happening in these images here, getting sort of fatty deposits in our vessels, and this can actually affect the resistance of the blood flow flowing through. And we can see here that the normal artery is actually free of the fatty deposits, but this one with the fatty deposits means we see there's a much smaller area for the blood to actually diffuse through. And this can actually cause and result in diseases such as pulmonary heart disease, atherosclerosis, and this is particularly bad in the coronary arteries, which can actually lead to strokes and heart attacks because the heart and certain body parts are being deprived of oxygen which they need, and therefore the blood not getting back to the heart properly means that we can't actually transport to the vital organs like the brain and the liver, and that means organs then start to shut down, and that's not what we want. So this is important that we actually maintain our health for these reasons. By exercising, we can actually raise the amount of proteins in the blood plasma, so that means we can remain and keep water, so the blood volume maintains the same. If we lose water because we're losing water by exercise, dehydration and sweating means actually it's going to become thicker. The water is what keeps the blood moving and sort of its liquid form. And it also increases the number of red blood cells, which we have said, and linking this back to elite athletes, they have a proportionally greater number of red blood cells. So this then enhances their ability to transport oxygen. And yeah, this allows them to work at that intensity.